How to debug quantum programming languages. Imagine trying to fix a puzzle where some pieces are constantly changing shape and others are hidden behind a curtain. That's what debugging quantum programming languages feels like. Quantum programs are different from classical ones because of the strange rules of quantum mechanics. When you measure a quantum state, it collapses, meaning you lose the original information. So, you can't just peek at the data like you do with normal software. Instead, you have to get creative. One common method is classical simulation. Developers run small quantum algorithms on regular computers to see if they behave as expected. This helps catch errors early, especially when working with a few qubits, which are the tiny units of quantum information. They also add assertions, like checkpoints, that verify if the quantum state matches what it should be. If an assertion fails, it points to where things went wrong. Tools like assertion-based debugging are gaining popularity. These tools can check the fidelity of quantum states using special tests called swap tests or compare measurement results to expected distributions. Even with the noise from real hardware, these assertions help spot issues. Quantum states are tricky because of the no-cloning theorem, which says you can't make perfect copies of a quantum state. But scientists have found ways around this with probabilistic cloning. This method allows partial copying with some chance of success, giving a peek into the state without destroying it completely. This is useful for debugging because it lets you observe parts of the program without collapsing the entire quantum state. Another approach is circuit slicing. Think of it like breaking a big puzzle into smaller sections. Developers analyze these sections separately to find where errors creep in. They can check intermediate states, but only within the limits of quantum rules. You can't just copy the state, so you have to carefully choose what to measure. Simulation tools are also vital. They let you run the quantum program step by step on classical computers. This shows how the quantum state evolves, helping you spot mistakes. But these simulations can be slow and requiring a lot of computer power, especially as the number of qubits increases. Quantum state tomography is another technique. It involves measuring many copies of the quantum state from different angles to reconstruct the entire state. While powerful, it takes a lot of resources and time, and the results are probabilistic. You need many runs to get a clear picture. Classical software testing methods are also adapted for quantum programs. Techniques like fuzz testing or mutation testing generate many different inputs to see how the program reacts. This helps find bugs that might not show up with standard tests. Since quantum programs are probabilistic, sometimes tests pass or fail randomly due to hardware noise. Debugging tools now include noise models to tell the difference between actual bugs and errors caused by the hardware. In the end, debugging quantum programming languages is a mix of classical techniques and new quantum-specific methods. Developers relying on simulations, assertions, and specialized tools to find and fix errors. It's a careful balancing act that takes into account the quirks of quantum mechanics and the limits of current hardware. As quantum technology advances, so will the methods to make debugging more straightforward and reliable.